All right, let's get back into it. So we're in the middle of section 7.1. So talk about this slightly new concept called a linear transformation. So again, a transformation is essentially, it is structurally no different than functions is the way you've thought about them. A function is something that takes an input, and for every input it takes, it gives a unique output. But now, since we're applying that to linear algebra, those inputs and those outputs could be like an ordered pair, ordered triple, things like that. So the last thing we did last time was talk about if a transformation is linear, then you should be able to replace it or re-express it as something like this. So if I multiply, my input vector, let's call it V. So if I multiply my matrix A by this input vector V, I should get an output vector. So basically the matrix multiplication does all the same process, does all the same work that the transformation does. So any questions on kind of like that's what we did last time. So if I'm telling you that a linear transformation can always be re-expressed as a matrix multiplication, should show you what that looks like. So this is essentially what we just did. So A is this matrix that stands in, or that is basically doing the job of our linear transformation. V, this right here, is some ordered basis. So if I multiply that vector A by this ordered basis, then what I get is basically a bunch of columns that are the transformation of each vector in the basis. So all these V1, V2, all the way up through Vn, these are the basis vectors of V tilde. So formalizing it now, but this is essentially what we did to that transformation we looked at the end of class last time. So we found A. At the start, we were given, what does this transformation do? To the vectors that come in, what does that transformation do? One thing we didn't talk about was what the basis is we're doing this with respect to. So here was our starting place. This right here is basically the recipe, like the formula for what this transformation does. We already went over the fact that this is linear. And what kinds of things does it transform? It transforms vectors in R2 into vectors in R3. But what's the basis we're using here? So if we're going from a basis of R2, how many vectors does that have to be? So we're trying to span two-dimensional space. And this one, the basis is kind of hidden from us. So I want to talk about specifically what it is so we can kind of generalize it to other questions. But let me ask it this way. So I want to come up with a basis for all of R2. So some number of vectors that I can combine in any way I can think of that can reach anything that looks like this. So basically a two-dimensional vector, xy. Do we have any idea how many vectors would be needed? Would it be two? Could we get by with fewer? Okay. So I think I agree with you that two vectors will do it. there are an infinite. So like I've said a bunch of times, a basis is not a unique thing. There are infinite number of bases for R2. So let's go with the simplest, maybe most intuitive one. So that's this thing I keep calling the standard basis. In the standard basis, basically every vector has exactly one in it. So hopefully, let me ask you this: do you believe that I could combine any number of these, or I could combine these in some way to reach any two-dimensional vector you could think of? So basically, the x-coordinate is going to tell you how many of this left-hand vector I need. The y-coordinate is going to tell you how many of this right-hand vector I need. So this is what we call the standard basis, or the canonical basis. And even though we didn't explicitly bring it up, this is the basis that we were implicitly using for this question yesterday. Because I'm telling you exactly how many x1s and x2s do I need to go from the input vector x1, x2 to the output vector that looks like this 3-row, 1-column thing. So if we apply this calculation we just looked at, so I said that A times V tilde equals TV1, TV2, so we only have two vectors. If the thing we're trying to solve for is A, how would we do that? How would we isolate A? Multiply V inverse on which side? Sorry, on. So you have to multiply on the left-hand side or the right-hand side? Yeah, we have to multiply on both sides of the equation, but I mean, am I doing this? Or am I putting that V inverse on the right? It has to be on the right or it won't do the canceling that I want. So if I multiply both sides by this V tilde inverse, this is essentially how we solve for A. If our V looks like the identity, then what does V tilde inverse look like? Let's remind ourselves of this thing. What does an inverse matrix do? What do you mean by one? Yeah, sorry. These special matrices called inverses. So let's say I have a matrix A that has an inverse that we call A to the -1. How are these two things related? If you multiply them together, you get the identity, right? So knowing that, what's the inverse of the identity? It is its own inverse. So we didn't go through this extra step of multiplying on both sides by the inverse, but the reason we didn't have to do that is because we were, implicitly dealing with the standard basis. So if this is the matrix operation I have, this isn't really what I want. What I really want is to isolate A. So to do that, I multiply on both sides or I right multiply on both sides by the inverse of the basis. So times V tilde, don't put a dot there. So in general, if we have a linear transformation, this is how we can find the matrix that essentially steps in for it. So I have to know these two things. What are the basis vectors? And then what does the inverse of that matrix look like? And also, what does the transformation do to all the basis vectors? So it might be it's subtle. We did all these things yesterday in that very last example, but it's probably hard to notice since the basis is just, you don't notice when you multiply something by 1, essentially. So let's look at something a little more complicated. We did that already. So now we're going to deal with a basis that's not standard. So the basis vectors now are basically what I'm acting on. So I'm telling you L is a linear transformation, and I'm telling you basically three things, three operations that this transformation does. So if I apply L to -3, 1, -1, it gives you 1029, and so on. So if these are these three operations we have, then we should be able to talk about what the basis is. What does V tilde look like? Maybe we should start with what order it's in. It's going to be a 3 by 3. So this is one thing that I don't think we've talked about. Maybe I briefly brought it up yesterday, but pretty much since we started talking about the idea of a basis up till now, we've talked about these things being, all right, these vectors are a basis for something, some subspace. We haven't usually cared about what that subspace is, just to say that it's the basis for something. They're linearly independent, and every set of vectors spans something. So all you really have to check for is linear independence. When we're dealing with linear transformations, we pretty much always want to span the largest thing possible. So we would really like for these three vectors to span all of R3. How can we make sure that's the case? If you reduce it, what should happen? If what I've just told you is true, that this is a basis for all the three-dimensional vectors, it better reduce to this. And hopefully some of you are finding out that that happens. True? Okay. So basically what we found is that this matrix I wrote down on the left and the matrix we reduced it to on the right, they span the same thing. And for the same reason, like we said something similar about the two-dimensional identity, the 2 by 2 identity. For the same reason that that spanned all of R2, this will span all of R3. But we would like to work with, so we're just checking that it spans all of R3, which it does. We still want to work with this weird basis, this like arbitrary basis we were given with, to figure out what the matrix representation of L is. So how do we do that? So we just talked about this, that AV tilde is equal to, so this matrix, if I stitch together all these columns, so T V1, T V2, T V3. So let's talk about orders again. We said the order of V was 3 by 3. What's the order of this matrix on the right-hand side? 2 by 3. So these, or hold on. I'm sorry, yeah, 2 by 3. So each one of these vectors, these TV1s, those are the outputs of these. So these are going to be these 10, 29, 31, 42, negative 17, 25. So each of these vectors is a single column with 2 rows. So this output is 2 by 3, which means A better be how big? Or what order? 2 by 3. So the threes need to agree, and then the outer dimensions dictate the order of the product. So we won't need to go through these checks all the time necessarily. I mean, when you're doing the homework and stuff on your own, you'll decide, like, you can decide what guardrails you want to check, things like that. But since we're just kind of getting started out with this, I want to know what size of matrix or what order of matrix I'm really trying to construct. So in this case, it's a 2 by 3. So I want to isolate A. How do we do that? Multiply V inverse on the right. So A V tilde times V tilde inverse equals this big matrix times V tilde inverse. What is this TV1, TV2, TV3? I guess I should be calling it L. But what does this matrix look like here? Right. So these are all the output columns. So 1029, 3142, -17, -25. I want to multiply this by the inverse of V tilde, which is the basis vectors all stitched together. So that should yield something. It's 2 by 3. Do we know that V tilde has an inverse? So if you've already calculated it, you've seen it. But the fact that we were able to reduce it down to the identity shows that there is something you can multiply it by to get the identity. So what's our final result for A? -387. Oh, sorry. So -26 is the first coordinate? Sorry, -26 is, okay, and then what was the next one? -226, -177. That bottom row has larger numbers than I remember. That's what I remember. I'm guessing there's a sign flip or something. So this is the matrix that defines this transformation L. So in this case, like the first example we did, like I showed you the recipe for what L does, for the incoming X1 and X2, or T. What T does, it does these kinds of processing. In this case, we didn't give you that like explicit recipe. We just gave you 3 data points, 3 input-output pairs. Any questions here? All right. So talk about this. I mean, this is the matrix, basically AV is what the transformation does. If you want to isolate A, talk about multiplying V inverse on the right-hand side. Did I already do that already? Okay, so now let's put one more wrinkle on here. Now I want to go between 2 bases. So I have B, which is a basis for R3, C is an order basis for R2, and I know what L does. So now I want to find a matrix representation of L. So how do we do that? How do we stack all these different components together? This transformation L, let's talk about its domain and its range. What kinds of vectors does it take in as inputs, and what kind of vectors does it deliver as outputs? It might be better to ask what kinds of things it delivers as outputs. What kinds of vectors come out of L? Yeah, so I have a single column with 2 rows in it. So it delivers something, or it maps something to R2. So what's coming in? How do you know it's R3? So each one of the things in the output vector they make explicit reference to X1, X2, X3. So it actually could be bigger. There could be more variables I'm not talking about, but I am describing this basis of R3. So that's what L does. It takes vectors from R3 and it maps them to vectors from R2. So if there is a matrix representation for L that we'll call A, knowing that it takes vectors from R3 and turns them into R2. So if I multiply A by a 3 by 3, and what comes out is a 2 by 2, does that give us an idea of what the dimensions of A are? Or wait, am I getting ahead of myself here? Oh, no, I'm skipping a step. I'm sorry. So let's think about what bases we have to deal with first. I know that this is what L is doing. We're going from R3 to R2. I'm going to deal with these bases one at a time. Which one should I deal with first? How come?
Because that'd be on the left side of the arrow.
Okay. So if I multiply B by something, for now, we'll just leave this blank. I'm going to get what? I'm going to get basically a list of columns here. BV1, BV2, BV3. So what is the basis that goes here? It's V, but so I'm going to call it V tilde. But do we know what that looks like? Like, can we define it? Or should we talk about what the dimensions of it are first? Do we know the dimensions of this matrix that's BV1, BV2, BV3?
Yes.
How big is that? Or what's the order of that? I don't think 3 by 3. I think it's 2 by 3. Because aren't we doing this transformation that makes this happen? So I think, yeah, it's going to have 3 columns, but I think each one of those vectors has 2 entries in it. So if this is 2 by 3, then I think vector v has to be, well, v is a basis, right? So it has to be square. How big is it? 3 by 3, which means b is how big? 2 by 3. I keep saying how big, not how big. It's the order. So we know what order object we're looking for b, but let's talk about what it is, or let's talk about what this basis is. What does this basis v look like? Well, let's look at L. I know that L, if I define a vector x1, x2, then the transformation is going to be -3 times the first component, +6 times the second component, +9 times the third component. Would you agree this is kind of like the very first one we did, or maybe not the first one, but this one here? We gave you the transformation kind of explicitly. For any input vector that comes in, we know how to process it. And because of that, we were able to say, all right, well, we can just kind of treat this as the standard basis. Because these coefficients, these are not with respect to some arbitrary basis. These are, purely 9 times x1, 4 times x2, and so on. So I think because of that, we can take the first part of this transformation as standard basis. So 1, 0, 0, 0, 1, 0, 0, 0, 1. If that's true, can we say what B is? Would you agree that B times V tilde is just going to be B? Why am I allowed to say that? So if V tilde is the identity, what do I get when I multiply B times the identity? I should be able to just get what B is. Just multiplying it by the identity is not going to have, it's not going to make any changes. So all I really need to look at then is stitching these vectors together. What do I get when I input a vector in terms of V1, in terms of V2, in terms of V3? That's basically what these transformations are. So, or what these coefficients are: -3, 6, 9, 5, -1, -9. So maybe in the margin here, I'll talk about kind of what we're doing. We started with V tilde, which is the standard basis. And then we converted that to the B basis. But we should also factor in how to get to the C basis from B. So the C basis is given to us. It is not standard. It's -8, 9, or sorry, -8, -9, 7, 8. So to find this matrix representation of L, basically I'm gonna have to have some combination of the standard basis, which is not going to have any material effect, this transformation B, and how I get to this basis of C. So in general, the calculation we're doing is this. We're saying the operation is AV tilde is equal to this matrix LV1, LV2, all the way up through LVN. But then if we isolate A, this is what we're doing. So A equals this calculation here. So far what we've done so far is to go from the standard basis to B. And in doing that, we basically use these explicit definitions to write down that matrix. We can't do that as easily anymore because we're going from some non-standard basis to a different one. But can we find out what happens if we apply this transformation to each one of these basis vectors? So let's go ahead and do that. Running out of room, but that's okay. What is L of -8, 7? How do we find that out?
We just plug it into the variable.
Yep. Oh, I'm sorry, it's not going to work. We need x1, x2, x3. Sorry. So, oh, why am I losing the plot here? Would y'all be offended if we cheated? Okay. So I'm losing track of what all the components are. What's that? Good. Why wouldn't it? So I didn't even have to admit to you that I was going to cheat. I disagree. I lie to my kids all the time. Like I told them that I didn't like the music from K-pop Demon Hunters, but I really do. Were you playing it? That's okay.
You gotta.
No, I really do. The music is very good. Okay, so let's look at the place I stole this from. So starting from the basis B, so B and C are ordered bases. L is this transformation that goes from R3 to R2. I think I started from the wrong place. So instead of looking at what how this transformation acts on the vectors of B, let's look at how it acts on C. So can I annotate on this instead? So let's define some of these pieces here. We're looking at each one of these individual vectors. So I'm going to kind of reverse engineer this calculation in the notes here. I'm going to multiply on the left by C on both sides. So what does this give me? C times L times VI subscript C is equal to LVI. So essentially what's going on here is this right here. These are the basis vectors from C. And if I multiply those by C, I get the transformation in the standard basis. So the way they've isolated is that we're trying to solve for what those basis vectors look like in C. So I'm pretty sure if you invert that, you just get the same thing back.
Yes.
Okay. So where are these values coming from? Negative 15, 10, negative 12, 5. Right. So if you run 5, negative 3, 2 through this transformation, well, I can't erase. So L of 5, negative 3, 2 is equal to negative 15, 10. L of 9, negative 5, 5. And if you want, you can verify each of these, but we know that L is a transformation that turns, or that maps three-dimensional vectors to two-dimensional ones. And then L, 129. So I know how L works on those three basis vectors in this basis B that spans R3. But in what basis are these three things here? So these negative 15, 10, negative 12, 5, 90, and negative 78, those should all be with respect to the standard basis. So that's a standard basis with respect to the standard basis of R2, but that's not the basis of R2 that I want to deal with. I want to deal with C. So that's why this is the thing we're trying to isolate, is this LVI with respect to C. So C inverse times LVI. So we essentially just built this thing here, LVI. So with respect to the standard basis, the matrix I get should be what happens when I stitch all those together. So negative 15, 10, negative 12, 5, 90, negative 78. So yeah, I'm sorry I got lost in the weeds here, or hopefully we're back to, or should we recap like what we started with and where we're trying to get to?
Yeah.
Yeah, so what did we start with? So we know a basis for B. This is a basis for R3. We're given this also a basis for R2. L is a thing that translates from R3 to R2. So what's the first translation we have to do? The first translation we did was this. We translated, and now I'm seeing exactly what I got wrong. We translated B to the standard basis. That's what these three calculations are. So I think that's one thing we can say, like I hate promising that every time something is true, but I think in general it's gonna be true that if you're given the transformation, like you're given a formula for the transformation, it's kind of that better be in the standard basis. Unless I tell you what other metaphorical language that's translated into. So by multiplying all of our basis vectors in B, or we didn't multiply, by applying this linear transformation L to all of my basis vectors of B, that got me to the standard basis. And let's be more specific, the standard basis for what? What size of space, or what order of space? R2. That gave me a bunch of two-dimensional vectors. But then I want to get from the standard basis for R2 to what? I want to get from there to this arbitrary basis that I gave you, this specific non-standard basis C. So how do I get from the basis vectors of B to the standard basis in R2? Well, I have to multiply it by something. What did I multiply it by? I multiplied B times, now I'll write this thing as an actual matrix. What size is B? 3 by 3? So I want to multiply it by something that yields what? What order should this product be? Because we're going to a standard basis of R2, right? So this better have 2 columns in it. But because we're multiplying 3 by 3, a 3 by 3 matrix times something, I think it's going to have 3 rows. So we're multiplying a 3 by 3 by something to get to a 3 by 2. So this matrix right here should also be a 3 by 2. So I'm not writing out B, but B is this 3 by 3 matrix that has all the basis vectors of B in it. What goes in this 3 by 2 here?
Like the corresponding L value.
Right. And so, am I wrong in the orders again? Why is it 3 rows, 2 columns? Do I need to transpose this? Can't be a 2 by 3. And I can't multiply them in any other order.
I have a question.
Yeah. Yep.
Why you got the answer? Was it just all the values from B?
Mhm.
Oh.
Yeah.
Then
Maybe I should just read it like this. So basically we're doing, let me erase some stuff. So we translated basically, yeah, all the vectors in B, right? Or not translated, transformed using L, right? And that gave us something in the standard basis for R2. But what were those things in the standard basis of R2 that it gave us? That was negative 1510, negative 12.5, 90, negative 78. So the question I'm trying to answer now is, if those are the coordinates, so basically that's the result of applying the transformation to the vectors in basis B, but those are all written in the standard basis. I need to figure out what are the what are the vectors in the, sorry, what are the coordinates in the basis C that got us here? So that's why we're doing this calculation here. I know what LVI is now. LVI is this. That's the result of the transformation when converted to the standard basis. But if I want to know what the coordinates in basis C that would have got me to the same point, that's why I need to multiply on the left by this inverse. So that's our final step here is, did someone say that they found this inverse was, or this matrix was its own inverse? Okay. I'll still write inverse because that is what has to happen. And I'm multiplying that by what? I'm multiplying that by the results of putting B through the transformation and coming out on the standard basis. So that right there should give us our final result, which is that. So we'll verify before we go any further. Yeah? Good.
So the goal is just to bridge the gap between the two.
Yeah, absolutely.
Convenience.
Right. And the most convenient way to bridge that gap is to, okay, B is something you never think in. C is a thing you never think in. Because why would you? They're just random things we came up with. So that's why the standard basis is a good middle ground to make translations to and from. So again, I'm sorry I boogered this thing up, but ask me all the questions. Let's try to repair. But Ryan, I think the way you sum this up is exactly what we did. We're starting in some basis that's strange. We want to go to some other basis that's strange. And the best way to get there is through the standard basis. Anything else? Go ahead.
So should we just like follow like this page of notes instead of like this page of notes?
Yeah, I mean, we can, now that we've kind of seen this, let's see if we can repair and recap. So here's what I'll do. I'll try to go back to this without losing contact. Oh, that's awesome. Dump it. Okay, none of this ever happened. So let's talk about exactly where we're starting and what we're trying to get to. So L does what? I know I've asked this a couple times, but let's take it again from the top. What does L do? It transforms from R3 to R2. So we could build the standard basis for any dimension we want, right? But if we're going from R3 to R2, what basis do we have to deal with? We could do standard basis, but if we don't do that, what else are we stuck with? Right now, what's the only basis I know for R3? B is the only one I can use, right? So I would like to know how L treats the vectors of B. And I need to do all of them because a basis is this minimal thing. In minimal, I mean that I need every single vector in that basis to span R3. So I need to know what L of 532 is. I need to know what L of 9, negative 5, 5 is. I need to know what L of 1, 2, 9 is. And in doing that, I translate from, so in applying the transformation L to the basis B, I get the transformation L, but in the standard basis. And you can't really say standard basis unless you talk about how big that basis is. Standard basis for what dimension of space? Cannot have a basis for 2 by 3. It's got to be square. R2, right? So I have gone from strange basis B to, which is a 3 by 3 basis, to standard basis R. Does it make sense that I went from three dimensions to 2? That is what we said that L does. So then what do I want to do? So now I want to know what L does with respect to C. So this is like a very basic schematic for this is my goals. So let's talk about how we got each one of these things. How did I find L of B? So basically I multiplied, and if I'm saying this is linear, I better be able to do the entire thing with matrices. So what did I multiply my basis matrix B? What did I multiply it by to get to? Do we gotta do this again, or did someone write down what the results were? That shouldn't take long. Negative 15 minus 30. Negative 27? Let's just go look at it again. Negative 15, 10, negative 12, 5. Nine, okay, I couldn't remember where the negative sign was. 90, negative 78. 98? Yeah, okay. What multiplication must I have done involving B to get to this? On which side? Okay, so what does that 2 by 3 look like? I can't erase those. Awesome. And what basis are these coefficients negative 3, 6, 9, 5, negative 1, negative 9 in? Right, but so yeah, that is what the function L does, but what basis are those coordinates or those coefficients coming from? So if this is the basis B, and these are the coordinates of L, in the standard basis of R2, then what basis are these coming from? These have to be in relation to the standard basis. So L, I need to find a different way to talk about these. So we're translating from the basis B to the standard basis of R2. So I don't think there's the right way to describe all these things and not give them the same name. Because really L has nothing to do with B. I'm just using L to transform B into something else. So what does L do? L goes from standard R3 to standard R2. If I multiply that by B, I get the effects of that transformation in R2. So then how do I get from there to L to the transformation with respect to C?
You multiply that by inverse C on the left.
Inverse C on the left. What can I erase here? So maybe we should just give names to all this stuff. So I have AB equals Y. And now I want to get C inverse on the left, both sides. So C inverse. What was the thing I was trying to solve for in all this mess? But yeah, so I want a matrix representation for L. But what matrix is going to do that? I mean, it's going to be a combination of a bunch of things. So basically what I have now is C inverse, which is a matrix that goes from the standard basis to basis C, times A, which is how we translated from, or this basically just describes the transformation L. C inverse times A times B equals C inverse Y. So I have a lot of different things going on here. Which one am I actually trying to isolate? I think at this middle step, we're at A times B equals Y, right? So we're trying to find the matrix representation of L, which basically encompasses, this whole flow chart. How did we end up getting there? Mm-hmm. Right. So I think in the end, what we want is this. I think we want C inverse times A times B. And that's going to equal C inverse Y, which this matrix Y we wrote down is, that's all on the standard basis. We're trying to get away from the standard basis in favor of the basis that's defined by C. So I think the final last step is to multiply both sides by C inverse on the left. So based on everything we have, I think L is given by this. L is equal to C inverse, which is -8, -9, 7, 8 inverse times A, which is -3, 6, 9, 5, -1, -9, times B, which is this given square. 5, 9, 1, -3, -5, 2, 2, 5, 9. Do all these orders match up? 2 by 2 times a 2 by 3 times a 3 by 3, which means L should be a 2 by 3, right? Has anyone got to the end of this? Okay, I think that's what you said. Did I get you right? I fell behind. Okay. So spent a long time on that, but I think it was all warranted. So hopefully we got back to a place where the sequence of steps makes sense for what we were given, what we were trying to get to. What else should we talk about? What other things that I muddied up can I clear up?
So based on the transformation, we could just transform which one would fit in there and then multiply by the inverse of the other. That's basically,
When you say would fit there, do you mean in terms of orders?
yeah.
In this case, I think that works because you're going from R3 to R2. So one thing that kind of makes your decisions for you in this specific example is that certain matrices will only be able to be put somewhere. But let's say, for example, we had a transformation T that went from R3 to R3. If that was the case, you'd be dealing with a bunch of square matrices, and you'd have to be more careful about what you're translating to what. What else? Yeah. Right. And the reason I was doing that is because I was translating incorrectly. Basically, I was going from one basis to another, but I was going in the wrong order, which is exactly why the matrix multiplication I was trying to do didn't work. What else? Good.
Can you gain dimensions so losing?
You can. So, for example, let's say this is a function, and I'll write it as a function, but you could write it as a matrix too. F of x is equal to x, 2x, 3x. So in taking a single variable, and you can translate it into three different. So in general, you don't have to go from larger dimension to smaller dimensions. They can be totally unrelated. What else? Okay. So that's the second to last section. So let's talk, I mean, we don't have a ton of time here, but let's get briefly into some properties of linear transformations. Probably just have time to kind of get into some of the vocabulary and tie it back to other properties of functions. So these are mostly terms I know you've seen, but let's kind of redefine them. When we talk about a functions, do we know what a function, do we know what the image is? Is that a word you've heard with functions? I wouldn't be surprised if the answer is no, but it's not something you typically use. Those of you that have heard it, what does the image of a function mean? What about the range? What's the range of a function?
All the values of x.
Close. It's all the values that come out, basically all the output values. So the range of a function are basically, if we think about functions in terms of inputs and outputs, the image is the full scope of all the outputs. The image is the exact same thing. So that's those, when you're talking about the concept or in the confines of functions, those words are used more or less interchangeably. The image of a function are all the things that you might be able to map to. If we say a function is 1-to-1, what does that mean? It's a little more than that, because by definition of a function is only a function if every input you give it gives only one output. So that's why, like, the vertical line test you've probably talked about before. If I draw you a graph here, is this a function? How come? What about this? No, I mean, there's lots of x values that if I draw a vertical line through it, that's why the vertical line test is a thing that works. That means that if you pick an x value, there are some x values that get mapped to a bunch of y values, which breaks a function. What makes a function one-to-one is the opposite is true. So this is not one-to-one because there are some y values that can be reached by multiple x values, right? So it's basically a horizontal line test. Something like this would be one-to-one though. Because no matter what, so it's a function because every x value you choose is going to have a y value that goes with it and only one. It's one-to-one because I can replace x and y. And it's true going the other way too. There's no way to draw a horizontal line through this and cross through that curve twice. So basically a function, a one-to-one function, that relationship goes both ways. What about a function that's onto? Is that something you've heard before? That one doesn't get talked about a ton. Basically, a function that's onto means that it reaches everything. So we just got done talking about transformations like this, right? From R3 to R2. If we say it's onto, that means that it can hit every single thing in R2. So I'll give you an example and counterexample here. Let's say it's a sine wave. A sine wave is not onto because there's a bunch of y values that it's not going to reach. But a straight line would be onto because it hits any y value you could think of. If anyone's ever heard of the kernel of a function, I'd be shocked. But what about the roots or the zeros of a function? When we talk about the roots of a function, what does that typically mean? For what?
It's either where x equals 0.
If I drew this, where are its roots? Every point across the x-axis, right? So a root of a function is where it equals 0, essentially. It crosses the x-axis because y equals 0. So why am I asking about all this stuff? We're not talking about those kinds of functions. Because basically we're going to talk about the linear algebra counterparts of all those things. So a linear transformation, again, it's a function. It's a specific kind of function that's represented in a specific way. But because it is a function, it has all the properties you would ever talk about with functions. So the kernel is the same thing as the roots of a function. So basically, the roots of a function are the inputs that when you put it into the function, they give back 0. The kernel of a transformation is the list of all the vectors that when I transform it, they send me to the 0 vector. So that's something we've done a lot of. We've called it the null space. If I'm looking at a matrix, I want to know what are all the non-zero, actually not all the non-zero vectors, what are all the vectors that I could multiply that matrix by and 0 comes out. So null space, kernel, say the same thing. If your transformation is one-to-one, then that means the only vector that gets sent to 0 is 0. The range, what are all the things your transformation can reach? That's the column space. So basically, if you take the column space of a matrix, what does the column space mean? Well, if I take all the columns as a vector, and I think about all the possible linear combinations of those columns, then that span is the column space. So basically, whatever all the vectors that belong to that output, that's the same as saying the range of a transformation, the range of a function. All the things in the output space. If the range of your transformation is literally everything, every vector possible, then your function's onto. its range is the largest it could possibly be. So let's go ahead and stop there. We'll do some stuff with the old/new vocabulary, or the old vocabulary spun in a new way. And then we'll finish up tomorrow.